So one topic that is a little bit more complicated than looking at typical monoprotic acid dissociations is the dissociation of polyprotic acids, where there are several protons that can come off successively, and each of those protons will contribute to the pH of the solution. So we're going to work through an example that's kind of fun because it allows us to calculate the pH of a raindrop in the absence of acid rain. If you're an environmental chemist and you want to understand the impacts of acid rain, you need to understand what the pH of an ordinary raindrop is first. So the example we're going to look at is the polyprotic dissociation of what's called carbonic acid, H2CO3. Turns out this is not the molecule that's existing in solution for the most part. You cannot go buy a bottle of H2CO3. What it actually is in solution is CO2 gas, carbon dioxide, dissolved in water, associated with water, and about 99.85% of carbonic acid is in this form. There's a little bit of these molecules floating around, but we can treat it as though it were this particular species. So this is going to be a shorthand for us in terms of looking at the acid behavior of this polyprotic acid. So let's look at the equilibria that we need to consider when looking at this carbonic acid in solution. And this is complicated. In a normal monoprotic acid, you have to consider the equilibrium for the dissociation of the acid, and then you also have to simultaneously consider the water autoionization. Now we have a more complicated case. We have a diprotic acid, H2CO3, that can dissociate to form protons or hydrated protons and HCO3 minus. There's a Ka acid dissociation equilibrium constant for this particular equilibrium. We call it Ka1 because that's for the first proton coming off, which is known to be 4.2 times 10 to the minus 7. Once that first proton comes off, the HCO3 minus that's formed can dissociate further to make more H plus and CO3 2 minus, carbonate ions. There's a second ionization constant for this second proton, which is 4.8 times 10 to the minus 11. Notice that Ka2 is much smaller than Ka1, and that's usually the case because pulling the second one off involves removing a positive charge from a negative species, which is going to be even harder than taking that first proton off. For this particular situation, these are dissolved in water. So there's one other source of protons that makes life even more complicated, and that is the dissociation of water to form protons and OH minus, and we know that Kw for this is our favorite 1.0 times 10 to the minus 14. So this looks pretty complicated. If I wanted to analyze this in detail, I could say, well, I start with some concentration of this, I lose a little bit of that, and from the stoichiometry, that means I form X moles per liter of H plus and X of HCO3 minus. But that means this is X, and of course this dissociates a little bit, and so I lose a little bit of that, and that means I'm creating Y over here and Y over here. But this is the same proton as that one, so really this concentration is X plus Y and Y plus X. There's only one group of protons in there. But life is even more complicated because I have water down here, and I can lose a little bit of water, let's call that Z, and I can form some Z over here and Z over here. But this is also the same set of protons, so this is really Z plus Y plus X. You can solve all of these things using a complicated set of linear equations. It's a royal pain, but it's doable. You can also be smart and say, let's make some approximations. This is small, this is much smaller, this is even smaller. So what we're going to do is we're going to first start by imagining that the main source of protons in HCO3 is from this first reaction. We're going to assume that X is much bigger than Y and bigger than Z. That will then give us values that we can use to solve the next biggest equilibrium constant, and then finally go to this one. So we're going to do this in a stepwise procedure. We'll assume that x is much greater than y and much greater than z. And in the end, we can go back and check this assumption and make sure we were right. So let's look at a problem that involves an application of this equilibrium to environmental chemistry. And let's ask the question, what are the concentrations of everything inside of a raindrop or rainwater falling through the atmosphere? We want to calculate what is H2CO3, concentration of H+, concentration of HCO3-, concentration of CO3 2-, concentration of OH-, and the pH. And as you'll see, we can actually do this rather simply for rain falling through the atmosphere with CO2 in it. So the first thing we're going to have to do is figure out how much H2CO3 is in the water that's coming from the dissolving of the CO2 in the air. So we know that these days the pressure of CO2 in the atmosphere is about 380 parts per million. That's part per million of atmospheres, and so that corresponds to 380 times 10 to the minus 6th atmospheres. So the next step in our analysis is to figure out how much of the CO2 that's in the atmosphere goes into our raindrop. So imagine that we have a bucket of water sitting out on the tabletop bench, and we have CO2 gas above this. This CO2 gas will be in equilibrium with CO2 dissolved in the water. It's primarily CO2 aqueous, but we'll write that as H2CO3. So we'd like to figure out how much of this dissolves in here and the concentration of H2CO3 inside of this beaker. And it turns out there's an expression for that. It's not really part of our first semester general chemistry, but it's something that you can learn about later on. And what that tells you is that the amount of H2CO3 or dissolved CO2 in moles per liter in solution is equal to a constant, which is like an equilibrium constant, times the pressure of CO2. This is actually called the Henry's law constant. This is something that is well known for CO2 in water. And the value of that is 0.034 moles per atmosphere. And since we know the concentration of CO2 in the atmosphere is 380 times 10 to the minus 6th atmospheres, this allows us to calculate the total concentration of H2CO3 in this beaker on the desktop or in a raindrop, and that's 1.29 times 10 to the minus 5 molar. What we're going to do next is assume that we can do what we talked about before in these equilibria and assume that the concentration of H plus is approximately equal to the concentration of HCO3, which we called X before, and that that's set by the first equilibrium. So now what we can do is use that first equilibrium expression, Ka1 is equal to H plus HCO3 minus divided by H2CO3, and use this approximation. The numerator we're saying is about X squared. We're going to assume that X is small compared to the total concentration of H2CO3. So I can just set this to the concentration of H2CO3 we calculated a moment ago. And this, as we've seen, is equal to that first Ka, which was 4.2 times 10 to the minus 7. We know what this is, put in the numbers, and what you find is that X is equal to 2.3 times 10 to the minus 6th molar. So this also justifies the approximation I made here. Turns out this is about 20 times bigger than the concentration of protons in pure water, which would be 1 times 10 to the minus 7 molar. So this little bit of CO2 that's dissolving in this raindrop is making it fairly acidic from that perspective. If I want to figure out the other species in solution that we asked for, now we move on to the second equilibrium. And we said that Ka2, the equilibrium expression for that, had the value 4.8 times 10 to the minus 11. And that, if you look back at the reaction, involves the dissociation of the proton from HCO3 minus. And so this would be the equilibrium expression for the second ionization. But we've just said that these two things are about the same, and so those cancel out. And it turns out, very simply, the concentration of CO3 2 minus is just equal to Ka2, 4.8 times 10 to the minus 11 molar. This is Y. This is what we called X. Notice that the value of Y is indeed much smaller than X, and so that approximation we made is a very good one. The last thing we need to do to finish our problem is look at the third equilibrium, which is the autoionization of water. And from that, we know that the OH ion concentration, one of the things we wanted to calculate, is the water autoionization constant Kw divided by H plus. This is 1.0 times 10 to the minus 14 divided by the concentration we calculated from the first dissociation equilibrium. And so this is 4.3 times 10 to the minus 9 molar. And so this is also a very, very small number. So our approximations are holding up well. And so we can summarize the H plus concentration is equal to HCO3 minus is equal to 2.3 times 10 to the minus 6 molar. This is set by the first equilibrium. The concentration of CO3 2 minus is 4.8 times 10 to the minus 11 molar. And the concentration of OH minus that we just calculated was 4.3 times 10 to the minus 9 molar. If I take this concentration of protons and calculate the pH, I get a pH of 5.63, which is indeed acidic. So even in the absence of things in the atmosphere that create acid rain, raindrops are acidic. It's sort of interesting in that if you go back before the Industrial Revolution, it turns out the pressure of CO2 then was smaller. It was 275 parts per million before the Industrial Revolution. And if you calculate the pH of a raindrop in the old days, what you find out is the pH was 5.70. So raindrops were less acidic before the Industrial Revolution than they are now. In addition, this is a small number here, but remember this is a logarithmic scale. So this corresponds to about 15% more protons in a raindrop now than there used to be. So this gives us the idea of the acidity or pH of a raindrop in the absence of environmental pollutants. Of course, there are things like SO2 that are emitted by coal-burning plants. SO2 can also dissolve in water to make sulfurous acid. And so if you want to understand the result of that for acid rain, you now have to do an even more complicated problem where you consider the dissociation of H2CO3 from the CO2 in the atmosphere, the dissociation of H2SO3 from the sulfur in the atmosphere, and that allows you to then calculate and understand the effects of acid rain. Life is even more complicated because if you're in an agricultural area, you also have ammonia from fertilizer runoff. That's a base that goes in and neutralizes some of the acidity that shows up in lakes and streams. But this is a kind of fun example of looking at polyproduct dissociation, and it's one that has relevance to atmospheric chemistry.